Okay, this is exam 1 from spring of 2010, Physics 102. In these first couple problems, you want to figure out the magnitude and the direction of the force acting on the minus 6 nanocoulomb charge. These are opposite signs charges, so they're going to have an attractive force. So the force is going to be in this direction, and it's going to have a magnitude given by this value, Qf equals K, Q1, Q2 over R squared. Let's figure out first what is the value R. That is the distance between them. And R is equal to the square root of 0.5 squared plus 0.5 squared, which is equal to 0.71. Then, just put in the numbers here, 9 times 10 to the 9th. Coulomb's constant, Q1, we'll call the 3 times 10 to the minus 9 coulombs, 6 times 10 to the minus 9 coulombs over 0.71 squared, and that gives us the answer, which is 3.2 times 10 to the minus 7 newtons. So that is option B. In the previous figure, what was the direction of the force? We've already listed the direction here, and we know that this angle is 45 degrees, and that's 45 degrees above the negative x-axis. But none of these list that. This is below the positive x, that's above the positive x, so neither of those is right. This is 30 degrees, so it must be this one, 135 degrees from the positive x-axis. Indeed, this angle is 90, this angle is 45, so this total angle here is 135 degrees from the positive x-axis, counterclockwise. Okay, number 3, it says we have a charged sphere, stationary electric field is 1,000 newtons per coulomb, and the electric field points down. There's two forces acting on it, the force due to the electric field and the force weight of the object, and we just want to set those equal. Fe is equal to Fw, that is QE is equal to m times g, and I want to know what is Q. It's mg over E. M is given, that's 1.2 kilograms times 9.8 meters per second squared over 1,000, and that gives us the value, which is 0.0118 coulombs. Now the charge on this particle has to be negative in order for the force to be opposite the electric field. So the answer then is minus 0.012, which is answer A. Let's see, this was D. Alright, if the charge on Q1 has a magnitude of 3 nanocoulombs, then what is the charge on Q2? Well, first we have to realize that the charge on Q1 is actually negative because the field lines are ending in the blue charge, the 3 nanocoulomb charge. So it's negative, so Q2 is going to be some positive value, and then we need to count the lines. There are 6 field lines going into Q1, and there are 3 times as many, 18, coming out of Q2. So that means that Q2 is 3 times Q1, and we've already said it's positive, so that's 3 times 3, which is 9 nanocoulombs. So that answer is C, positive 9 nanocoulombs. Consider these two separate arrangements of insulating materials. If Q3 has a negative charge, what is the charge on Q1? Well, if Q3 is negative, Q2 is the opposite, so Q2 is positive, and then Q1 has to be the same. So the answer is that Q1 is positive. Two charges experience an electric force of 20 newtons. If the distance between the two charges is doubled, what is the new force on the charges? Okay, well, we know that our force is K, Q1, Q2 over R squared. If we double this distance, then that makes our force go down by a factor of 4. So our force was initially 20. 20 divided by 4 is 5. That's D. Okay, consider these two charges. Where on the x-axis can a third positive charge be placed such that the net force on that charge is 0? Okay, there are only 3 places it can be. To the left of minus Q, in between minus Q and 3Q, or to the right of the 3Q charge. Now if we put a positive charge here, the forces that are acting on it due to the 3Q charge, they're a similar charge, so it's repelled, and it's attracted to the minus Q charge, so that's not equal to 0. Now if we put it over here, close to the 3Q charge, this is plus Q, it gets 2 forces acting on it. Due to the minus Q charge, it gets a force in that direction, and due to the 3Q charge, it gets a force in this direction. Now, this is not 0 because the force due to the 3q charge dominates the force due to the negative q charge, because it has a bigger charge and the charge is closer, that is, this charge is closer to the 3q charge. So that just leaves the last option, so let's just try that. If we put our charge over here, it feels an attractive force to this charge and a repulsive force from the 3q charge, but since it's further away from the 3q charge, that force is less than it is over here. So these two forces can cancel out. So the answer is it has to be to the left of the minus q charge, which is A. Which of these is not an allowable charge? We know that the fundamental unit of charge is 1.6 times 10 to the minus 19 coulombs. This one, it would be the equivalent of 1.5 protons, and so that is not an allowable charge. This one, by the way, is allowable. It's just really a matter of significant figures. I don't know enough significant figures to tell me if there is a fraction of a proton in that charge, because 25 coulombs is a whole heck of a lot of charges. It's like 10 to the 19th charges. So that we assume that that is a round number of protons, a whole number of protons rather. Which vector in this figure best represents the direction of the electric field? Well, due to this 10 nanocoulomb charge, the electric field is in this direction, and due to the 20 nanocoulomb charge, the electric field is in this direction, but it has twice the magnitude of the 10. So if I add those two vectors, I get the answer D, vector D. 1 electron volt is the kinetic energy that an electron requires when it accelerates across a potential difference of 1 volt. Now we said that the potential energy is equal to Q delta V, and in this case we have a charge, an electron, accelerating across a particular potential. So we can set this potential energy equal to its kinetic energy. Before it starts accelerating, it has this potential energy, which is Q times delta V, and then that's all converted to kinetic energy. So Q delta V is equal to 1/2 mass times the speed squared. And then we want to know what V is, so that's equal to the square root of 2Q delta V over M. So that's equal to the square root of 2 times 1.6 times 10 to the minus 19. This is an electron, but we're just worried about the magnitude of the speed, so I'm going to leave the negative out. The delta V is just 1 volt. And the mass of an electron is 9.11 times 10 to the minus 31 kilograms. And that gives me the answer, which is 5.9 times 10 to the 5th meters per second, which is option A. In this figure, an electron sits between two charged plates, and the electron moves to the right, so it feels a force to the right, and the force on an electron is the opposite the direction of the electric field. So I know that my electric field must be going to the left. And so that's the direction of the electric field between the plates, option B. What is the potential at point B if Q1 is plus 2 and Q2 is minus 2 microcoulombs? We want to know the potential here. Potential is equal to the potential due to 1 plus potential due to 2, which is K times Q1 over R1 plus K times Q2 over R2. Now let's figure out what our R's are. This is R2 is 4 meters. This distance, which I'll call R1, is 5 meters. This is a 3, 4, 5 triangle, so it's equal to 5 meters. If you don't remember the 3, 4, 5, this is just equal to the square root of 3 squared plus 4 squared from the Pythagorean theorem. Now we just put in our values here. I'm going to factor out the K and the Q. So I'm going to have I'm just going to put in the numbers. 9 times 10 to the 9th times Q. 1 and Q2 have the same magnitude, so it's 2 times 10 to the minus 6 times 1 over R1, which is 5, minus 1 over R2, which is 4. This negative comes about because Q2 has a negative charge. And so when I factored out this 2 times 10 to the minus 6, I left the negative in there. So that gives me the answer, which is minus 900 volts. You don't have to do this factoring. You can just put in the numbers here if the factoring confuses you. Just put in the appropriate numbers. K is 9 times 10 to the 9th. Q1 is 2 times 10 to the minus 6. R1 is 5. R2 is 4. And Q2 is negative 2 times 10 to the minus 6, and that will still give you minus 900 volts. But the calculation is a little easier if you factor it out. So let's see, that was option B. Alright, the capacitor is hooked up to a battery with a voltage of 12 volts. After charging the capacitor, the battery is removed. What is the voltage across the capacitor if the area of the plates is doubled? So you charge it up to it with a voltage of 12 volts. And then when you take the battery away, that means that the voltage remains, or excuse me, the charge remains constant. Now we know that Q is equal to CV. So if we change the capacitance, that's going to change the voltage. So by changing the area, we change the capacitance. Capacitance is epsilon naught A over D. We are doubling the area of the plates, increasing it by a factor of 2. That means the capacitance increases by a factor of 2. So the voltage has to go down by a factor of 2, in fact. So the final voltage is 12 volts divided by 2, which is 6 volts. And that's A. Okay, these 6 charges are at the corner of an equilateral hexagon. What pair of statements best describes the electric field and the potential at a point in the center of this hexagon, equidistant from each of the charges? Well, to check for the V, we just want to see that there are equal numbers. If there are equal numbers of positive and negative charges, then the potential is equal to 0. We have 2 negative charges and 4 positive charges. That means that the potential is not equal to 0. In fact, it's greater than 0 because there are more positive than negative charges. And then to figure out the electric field, we just draw the electric field vector for each one. I'm going to begin with this charge right here and go clockwise. The electric field due to this charge is away. It's in that direction. The electric field due to this charge is in this direction. The electric field due to this charge is in this direction. Due to this charge is in this direction, and due to this charge is in this direction, and then due to this charge is in that direction. To find the direction of the electric field, you ask yourself, what would be the direction of the force on a positive test particle at that point due to the charge that you're considering? And that direction of the electric force is the same as the electric field. So you see, we have equal vectors that all cancel out, so that means that the electric field is equal to 0, and that's option B. The following graph is for potential versus position. If a proton is released at point x equal a, what direction will it move? So you have a proton that's at this point, and the proton wants to move from high to low potential. However, at this point, you can't move from high to low because you're at the lowest point. So that means that the proton will remain stationary. And that is answer A. What is the equivalent capacitance of this circuit? Alright, well first we want to add up these. That's 1 over 1 over 2 plus 1 over 2, and that's equal to 1. And then we add up this equivalent capacitance. If we get rid of these, this is just a 1 microfarad capacitor. So then we add up these, which gives us 1 plus 3, which is 4 microfarads. And so this circuit simplifies to a 4 and a 4 microfarad capacitor, and the equivalent capacitance of that is just 1 over 4 plus 1 over 4, and that's equal to 2 microfarads. And that is A. Alright, a capacitor of 3 microfarads is hooked up to a 10 volt battery. How much energy does it have after charging completely? Well, energy is just 1/2 CV squared, just plugging in here, 1/2 times C, which is 3 times 10 to the minus 6, times 10 volts squared, and that gives us the energy, which is 1.5 times 10 to the minus 4 joules. That's option C. Alright, we have 3 charges. We want to know how much work is required to assemble these charges. You want to start and place the first charge. I'll call this Q1, that's this charge up here. To put this in place, the work is equal to Q1 delta V, which is equal to 0. Now to put Q2 in, this distance is R. The work to place it here is Q2 delta V. That is Q2 times K Q1 over R. And then to put the third charge, these distances are all R, this is Q3. The work to place it here is equal to Q3 times delta V, which is Q3 times K Q1 over R plus K Q2 over R. Now this is work 1, work 2, work 3. The total work is just the sum of those. Alright, but because the Q's are all the same and the R's are all the same, I can add up these 3 values, 0, this, and it's just 3K QQ over R, because Q1 is equal to Q2 is equal to Q3. And if I put in those values, that's 3, 9 times 10 to the 9th, 3 times 10 to the minus 6, and this is squared because the two Q's are the same, and R is 0.1 meters. And that gives me a work of 2.4 joules. So that's the answer, which is D. Alright, what is the voltage across the circle capacitor in this figure? Well, we know that the equivalent capacitance of this is 2 microfarads. So if I were to replace this with a capacitor, it would be a 2 microfarad capacitor. So we have a 2 microfarad and a 2 microfarad splitting the potential of 10 volts. So that means I have 5 volts across this and 5 volts across this. Now the 2 microfarad is actually two 1 microfarad capacitors that are in parallel, but capacitors in parallel have the same potential, so they both have 5 volts. So the answer is C. Two wires A and B are made of the same metal and have equal length, but the resistance of wire A is 4 times the resistance of wire B. That means that the diameter of A has to be less than the diameter of B. Because its resistance is greater, the diameter has to be less. Now we know that R is equal to rho L over A, so R has an inverse proportionality with area, and so we know that the area is going to be the area of A is going to be 1/4 the area of B. But since area is proportional to the diameter squared, then we can say that the diameter of A is 1/2 the diameter of B. And that's option D. That was straight from the concept test. Which of these has a greater resistance, an incandescent light bulb or a bathroom heater? You're supposed to realize that the power of a bathroom heater is a lot more than the power of a light bulb. It gets a lot hotter, so it has a lot more. It's a lot higher power rating. So, for example, the power of a bathroom heater can be on the order of 1,000 watts. And that's a lot bigger. And since P is equal to V squared over R for a constant for a given current, the smaller the resistance, the bigger the power. And we're looking for the greater resistance, so the opposite is true. The bigger the resistance, the smaller the power. So the one that has the smaller power is the greater resistance. So that's the light bulb, which is B. A 1 volt potential is observed across a 10 ohm resistor. What is the current? Well, I is just V over R. That's 1 volt over 10 ohms. That's 0.1 amps. That's answer A. Alright, when you apply a potential of 3 volts to a particular electrical device, the current is 2 amps. When you apply 6 volts, the current is 3 amps. Is it ohmic or non-ohmic? This is not a linear device. You see that with 3 volts, your resistance is V over I, that's 3 over 2. But then at 6 volts, our resistance is equal to 6 volts over 3 amps. Okay, so your resistance is changing as your potential is changing. So that is not ohmic, non-ohmic. It's A. Okay, current of 20 amps flows through a wire of 1 meter and cross-sectional area is given. The potential across the wire is 1.4 volts. Select the material from this table. Resistivities. We know that R is equal to rho L over A. So I'm going to solve this for rho. It's equal to R A over L, which is V over I times A over L from Ohm's law. I put in my values, 1.4 over 20 times 7.85 times 10 to the minus 7 over 1, and that's equal to 5.5 times 10 to the minus 8 ohm meters, and that's tungsten from this table. 50 ohm resistor is hooked up to a power supply of 150 volts. What is the power? P is equal to V squared over R. Easiest way to do this is 150 volts squared over 50 ohms, and that gives me 450 watts. And that is B. And this was version C of the test.